Okay, so I will start with some information on state of the art. And I just put this first slide so that you can actually appreciate how the things have changed through time. So our knowledge has changed through time. So on the right, you can see a beautiful SEM images by Jeremy Young of Helicosphaera carteri. And on the right, you can see a beautiful drawing made by Wallich in the 19th century of the same species. So something has changed in our knowledge on calcareous nanofossil. Why they are so important? So basically, they are so important for two main reasons. One is because you can actually use them as a paleoecological indicator, paleoecological tool in the reconstruction, because they lies at the base of the food chain and they play a fundamental role in the carbon cycle, biocycles. But we will avoid this part. That is a very great part, and we will focus on the second part, on their importance as a biostratigraphic tool. So I put this slide just to highlight one of the most important requisites that any group should have if they want to be a very good stratigraphic tool, biostratigraphic tool. So the high evolutionary rates. This is actually a modified version of a very famous figure made by Paul and co-authors in 2004. And here you have basically time. So from the Triassic to the Neogene on the y-axis. And the most interesting thing is what is graph here, is plotted here, that is the species richness throughout all this interval. And as you can see, during the Jurassic and the Cretaceous, you have an increase that peak at the KPG boundary, where we all know the calcareous nanofossil were affected by the KPG mass extinction. And then they return back to quite high species richness values. But the more important thing in this figure is these two lines. So the speciation rate that you have in very dark blue and the extinction rate that sum up make basically the the evolutionary rates. And in this case, we can actually see that calcareous nanofossils have high evolutionary rates. Another important requirement is that any group should be widespread. Calcareous nanofossils are a planktonic organism, as all of us basically knows. So they have a widespread biogeographic distribution. And sometimes even more importantly, they are usually high, they show a very high abundance in the sediments. So basically, at least in principle, they are a very good biostratigraphic tool. So here I prepare like a scheme of the four phases that I have actually identified in the story of the study of this group. So a first phase that is here in purple that I call pivotal, in which basically you can actually see that all the main and more important works were focused on the description of new species, so on taxonomy basically. And this phase is focused basically on occur in the 50 and 60. And then you have a second important phase in which that I call biozonation, in which the two standard biozonation was published, and this occurred in the 70 basically. So that in this time, during this time, we actually were able to produce a more structured biostratigraphy. And then the third phase that I call review, and I put just an example for give you an idea. That is the review that is in plankton stratigraphy that we all know by Perch Nielsen, that dated back in 1985. So this basically is the window of this phase, the 80s and the 90s. And then the last one. So the last phase basically occurred in the 21st century, and is basically characterized by the idea that you also need, biostratigraphy is good, having a firm biostratigraphic framework is good, but we also know the ages of our biohorizon. So biostratigraphy should be implemented with biochronology. And this is a slide. I'm not going to detail because it would be a nightmare for everyone. But it's just showing the two standard biozonations. So the one that I actually just mentioned you, the Martinez and the Okada-Bakri biozonation. And as you can see, they are able to subdivide the entire Cenozoic. But it is not all, everything is that this shown here is not without any problem. So the thing is that there are pitfalls in this biozonation, this standard biozonation. What are these pitfalls? So I identify more or less 4 categories. The first category deals with ambiguous taxonomy. That is important, and we will see why. I will give an example for each of these categories. And then the low reliability of biohorizons. So, for example, the question that Abel just made, so about the synchronicity of biohorizon. And then the low standardization of counting methods or estimation. And finally, we will see that there are periods of time in the Cenozoic in which the duration of some biozone is really, really long, maybe too long. So starting with the first category, the taxonomy, I will make an example of what I mean. So here you have the images, the original images in the original description of 2 very well-known species. On the left, you have Discoaster lodoensis, and on the right, you have Discoaster sublodoensis. So the names are pretty similar because they are pretty similar, also morphologically speaking. And as you can see here, I put the main morphological feature for the 2 species. So you can see that for lodoensis, it can vary in terms of rays that are this kind of a feature in this cluster from 5 to 8, rarely 8 rays, and they could vary a lot in terms of size, so from 12 to 24. What about sublodensis? It varies in terms of size from 4 to 6, so there is a kind of overlap. And there is a kind of overlap also in terms of size, because, it's smaller, but there is a kind of overlap. So these 2 end members, they are quite clear. I think that I can make the point that they are different. But what about this guy in the center of the slide? So it has 6 rays, and the size is 12 microns. So how we can solve this kind of integrated morphology that create ambiguous taxonomy? So one possible solution, the one that we have actually decided to adopt it, since we are paleontologists and we are not dealing with DNA, but we are dealing with morphology, we have decided that we just include in this group, so in Discoaster sublodoensis, the 5 raid, and all the others goes to or will be ascribed to Discoaster lodoensis. So then now you have a very clear taxonomic concept, and you can use these species actually to as a marker of a biozone. The second category, the reliability of biohorizon. So this is, again, a slide. I just skip a little bit what I was trying to say. But anyway, this is a slide just to show you how the biozone are described. But the more important thing is that you remember that biozone are defined by a base and by a top, by different kind of biohorizon. And based on the fact that you use different kind of biohorizon, the names of this biozone are different. But we will concentrate on the biohorizon. So especially I will provide you an example. In this case, to prove my point, is the case of Discoster multiradiatus. Discoster multiradiatus is a late Paleocene, early Eocene species. And here I provide you at least 3-4 data set from the Atlantic, from the Tethyan Ocean, and from the Equatorial Pacific. And what I would like to tell you, to show you, is that if you start from this part of the slide, so from ODP site 1262, is that we have in blue the abundance pattern of this guy, so of this Discoster multiradiatus. And it appears somewhere in the section and goes up to the section. So the lucky thing is that we have PMAG data, so that we can actually liaise these bioevents with PMAG. And if we do the same game with the other section, we can see actually that the Discoster multiradiatus appear in the same position in the Equatorial Pacific and appear in the same position also in the Tethyan Ocean. So it appears that at least in terms of synchronicity, this event is a very reliable event. So we need this kind of biohorizon instead of the poor one to define our biozonations. Another pitfall, the third category, is the standardization of counting methods. The standardization is both in terms of quantitative, qualitative counts and high versus low resolution counting. So here you have two figures. I will start with this one on the left, in which I will show you the abundance pattern of an idealized species A. So it's not real. It's an ideal pattern. And in this case, in the first case, you have a quantitative abundant pattern, so the number of specimens per millimeter square. But if you go to the right, you have something that we know quite well. That is the range chart that is based on a different approach, so a qualitative estimation of the abundance. And finally, you have the absence-presence diagram. So basically, it's based on the absence and presence of the taxon. And I think that it's quite easy to understand it, that if you go from the left to the right, you are losing information. So it is important and crucial to standardize counts, but in terms of quantitative estimation. If we move now to the right, again, this is an idealized abundant patterns of a species A. And on the left, on the left, you can see the abundance pattern of a taxon species A in a very high resolution. So there are a lot of points here. And here you have the same data set. I just use 1 to 10 of the sample that I analyzed. And this is the result. So what is the message here? The message here is that if you look at this taxon is perfect. It's abundant, it's continuous, it appears sharply. But if you go here, you can see a different story. So we have to standardize counting methods, but we have to prefer high resolution. Finally, the fourth category was on the biozone duration. And I put this scheme that comes from Raffi et al. And put together the most recent biozonation for the Paleogene here in orange and the Neogene here in yellow by Bachmann et al. 2012. And as you can see, there are some intervals in which we can actually do better because, for instance, in the Oligocene, the duration is extremely high. but also in some intervals of the Eocene and in some interval of the Miocene. So we can actually improve this point. Okay, so finally, I will just introduce a new biozonation. It's not new because they have been published for 6 years now. But anyway, there are two new biozonations that are available from the literature, and they have a kind of different approach from what we have seen from the standard zonation. So the first approach is a multi-site approach, so that you can actually see from this slide that the data set, that is a complete data set, as you can see here. So the bar just represent the sites, so we use the different sites to cover the entire Paleogene in this case, and in the bottom part of the slide, the Neogene. And as you can see, the size comes from basically middle to high latitude. And this is the final results of this, so this new biozonation. And this is also the fourth phase. So the integration between biostratigraphy and biochronology. So here you can actually see that you have the integration of different biozones, but also you have the integration with the chronostratigraphy, with PMAG, with the GPTSO, and the age, so the chronology. And this is available for the Paleogene and for the Neogene. Just a couple of more minutes, try to focus on some possible future perspective and possible implementation. So I put some points, and I think that I made my point that we need to standardize the methodology, because if we standardize the methodology, the data set are of high quality. I think that I made also my point that an ambiguous taxonomy can help a lot in using taxa that, at least in the past, have or have had an ambiguous taxonomy. We also can implement the biostratigraphic framework. So I actually just show you that there are some intervals in which the duration of the biozones is quite long. We can improve this. Another thing that we can actually do is to improve the available biochronologies by using an astronomically tuned age. And another important point is just looking outside our windows is to integrate calcareous nanofossil data with other groups. First of all, calcareous plankton groups as plantic forams, but possibly other groups like radiolaria and dinoflagellates. Other important fundamental points. All I've shown you is valid for mid to low latitude and open ocean. The problem is that when you try to correlate between shallow water and deep water environments, you can have some issues. As you can have some issue in correlation between low and middle latitude and high latitude, because they are different domains with different assemblages. And then we have to try to integrate with a paleoclimatic proxy, as for instance, the nice example Juliana just made. But I think that more importantly, I think that we all had to change our approach as micropaleontologists, that is of being just a data collector, nothing more than a data collector, and change into a more interdisciplinary approach, so that we will really able to give our fundamental contribution that is not just the age of the sediments, for instance. And it's important that we try to actually give this fundamental contribution and discuss with other scientists. And I think that is all for me.